bit of a step back here. We're going to think a little bit more about the second law in the rate equation form, whereas last lecture we were kind of looking at it from a whole system perspective. But we're going to zoom back into the rate form just to kind of go over the different ways that we can fix or find the specific entropy of different types of fluid. Now, for a lot of this, it's probably just what you would have guessed, but particularly when we start to talk about ideal gases, there's different rules that we use, right? Or different methods that we're going to use, right? So we'll start here with the second law rate equation, right? So hopefully this isn't new to anybody at this point. We know that the reason we do the math of this equation is to find out what's going on here with the entropy generation rate, or sigma dot. We know that real processes generate entropy, so the entropy generation rate must be positive. We know that the very best we could approach, but not actually do, is the ideal process, where that entropy generation rate is 0, sigma dot. And if we ever do this and we find that sigma dot is less than 0, that means that the process is not possible and that it's violating the second law of thermodynamics. But in order to do this, in order to do the math for this kind of problem, we'll certainly have to fix the states here. We'll have to figure out what the specific entropy at all the inlets and all the outlets are. Now, we've done a couple problems like this, usually dealing with something like water or refrigerant, but I don't think we've talked about how to do this for ideal gases yet. But I'll kind of go through all the different types of fluid you'd see in this class, and we'll talk about how to find specific entropy, right? So just like H, right, when we're trying to find the specific enthalpy, or when we're trying to find specific internal energy, the question that we need to ask ourselves is, what's the fluid, right? So we can have water or something like it that's kind of bouncing back and forth across the vapor dome, or we can have an ideal gas. So we'll start with water because it's pretty straightforward, I think, generally, to find specific entropy in water or refrigerants, because it's basically the same as all the other properties that we've found, right? So here, if we're above the vapor dome and to the right, we have a superheated vapor. We're just going to look this up on a table in exactly the same way you would find H, right? It's just that S is the next column over to the right. So you're still going to find that interpolation factor that I've been calling A. If you're halfway between, say, 520 and 560 degrees, then you'll go halfway between whatever the values in those rows are for the specific entropy. So that one hopefully is not too hard. Under the vapor dome, it's also the same, but now we're going to interpolate with quality, right? So again, we're going to look at the table, and now instead of looking for U or H, we'll just bump down a couple columns and we'll look for SF and SG. So the specific entropy of the saturated liquid, that's SF, and the saturated vapor, that's SG. And we've seen how when we talk about quality, we're just taking a linear combination of, what's the mass fraction of the liquid and what's the mass fraction of the vapor. So again, nothing new here, except we're taking values from a different column in the chart. In the textbook tables, there is no SFG in the tables. They only give you HFG. So you have to do the subtraction here of SG minus SF. Subcooled liquids, right? So here we're generally going to use the same strategies that we use for subcooled liquids for U or H, right? So we could do some kind of double interpolation here, right? Or we can say that this is actually, so there's three strategies, I guess. Double interpolation, which probably you won't do unless the pressures are very, very high, because you need the tables. And the subcooled liquid or compressed liquid tables usually don't start till you get very high pressure. So you probably won't do that. If you're just fixing a state. You're not going through something like an ideal pump or something. You can look at and you can say, well, SF is going to be approximately equal to S of what we're looking for if we match up the temperatures. But the other thing you can do, remember how we have equations where, delta U is equal to CV times delta T, or delta H is equal to CP times delta T. Well, it turns out that we have a similar equation for trying to find specific entropy. Here we take delta S, right? S2 minus S1, still going to be CP for specific entropy, right? And then we're going to take the natural log of T2 over T1, right? So not the temperature difference like we would if we were trying to find delta H, but the natural log of the temperature ratio. Now the order here is important. When you have S2 minus S1, the first number goes in the numerator here in the natural log term, right? So we go S2 minus S1 becomes CP natural log of T2 over T1. Right, so it's kind of like CP times delta T, right? So you can use that if you're in the subcooled liquid region and you don't want to use a table, you have a specific heat, you want to use a constant specific heat assumption, then you can do that with subcooled liquids. But once you get into, even under the vapor dome, anytime there's any kind of vapor in your system, you can't use that equation anymore. Now, things get a little more complicated when we talk about ideal gases. So with ideal gases, we have some options. So just like with H, we can use table A22 in the textbook, right? So this is a variable heat. If you're doing variable specific heat analysis, then you'll have to use table A22. Now, table A22 is a little bit weird when we look in the textbook here because it's not going to give you the specific entropy. So this is something that people sometimes mess up. On table A22, there's a column that has little s superscript 0, right? So what that tells us, it's kind of telling us what's the change in the specific entropy due to the change in the temperature, right? So this is kind of like the temperature part of the change in the specific entropy. But we can also get changes in the specific entropy because of the pressure, right? Because the gas is compressible. So then we have to add this second part. So that's negative R. Remember, R is the specific gas constant, which will be the universal gas constant divided by the molar mass. Now again, we have this natural log of something over something, but this time it's P2 over P1, right? And again, state 2 comes first in our delta over here, so state 2 goes on top in the numerator in the natural log term. So that's if we're doing a variable specific heat analysis, and we can only look up on table A22 or table A23, depending on what the gas is. You can only look that up. You can only get the S superscript 0 terms. So I think sometimes on tests, when people are going quickly, they will think that delta S is equal to delta S superscript 0, and that's not going to be the case unless your pressures are equal, right? Because the specific entropy is a function of temperature and pressure when we're talking about gases, so we have to look at both, right? So we need something about temperature. That's what S superscript 0 tells us, something about temperature, and something about the pressure. That's what this other term tells us. Right? So this equation is on the equation sheet as well, right? So this superscript 0 term sort of tells us what's the change in the specific entropy because the temperature is changing, but then we still have to fill in some information about what's going on with the pressure. So that's the variable specific heat option, right? Anytime we ask what's the fluid and the answer is, oh, it's an ideal gas, then we have to decide, are we going to do a variable specific heat analysis or a constant specific heat analysis? And the good thing about the constant specific heat analysis is that we don't need information from the tables, right? Or at least we don't have to interpolate to find something like S superscript 0. So now it's still, this specific entropy is still going to be a function of, for open systems, temperature and pressure, but for closed systems, we'll talk about temperature and specific volume. But if you were dealing with an open system and you had an ideal gas and it was constant specific heat, this equation looks the same in that it's got something to do with the temperature and something to do with the pressure. But instead of having that delta S superscript 0 term, then we replace that with Cp times ln T2 over T1. Right? I think I maybe said this before, but when we grew up, we called it ln. I don't know if that's a Canadian thing or just a 90s thing, but I think we've moved on from there. So if you hear me say that, I'm not talking about my grass. Right, so the Cp times natural log of T2 over T1 minus R times the natural log of P2 over P1. Again, the first number in our delta, the state that's associated with the first term, always goes in the numerator. The other thing that I haven't been saying here is these are not temperature differences in the numerator or the denominator. So they have to be absolute temperatures. They have to also be absolute pressures, but typically the numbers we'll get in problems are absolute pressures already. So, but make sure you're using absolute temperatures and absolute pressures here. Now for closed systems, like the systems we were doing earlier, piston cylinder type problems, we won't necessarily know the change in pressure, and maybe we know the change in specific volume. So it turns out that here you can also use constant specific heat analyses, right? But now it looks a little different, right? Now the way that I kind of remember this, although it's on the equation sheet, so that's the best way to do it, right, is that for open systems, we're normally talking about pressure differences and also delta H, and delta H is Cp times delta T. So that's, I remember that Cp is the one that's in the one with pressure. And Cv we use typically when we're talking about volumes, right? So notice that here, this is the volume is going in there, right? So this is Cv times the natural log of T2 over T1. Now these two terms here look almost the same, right? But we've swapped out pressure for a specific volume, and the sign of this term changed from a subtraction to an addition over here, right? So again, you look at the information that you have or the information that you can figure out, and you pick the right equation. So when we're talking about open systems, when we're talking about variable specific heat analysis, we have to remember that the accuracy of that type of a problem or that type of a solution method is higher than constant specific heat. So they'll be pretty similar in accuracy as the temperature differences are small, but as the temperature differences get bigger and bigger, these constant specific heat equations, step further and further away from reality. Right, so if you have an application where accuracy is the most important thing, then you may want to revert back to using the tables instead of these constant specific heat equations. But again, on an exam, I'll tell you whether or not I want you to do constant or variable specific heat. So you can find these things in the equation sheet, but they're also, this is, I think, taken from the FEE handbook here in the US, or at least the version that was around in 2016 or something like that, whenever I made this slide, right? But these are just the same equations. So you can pull these up and take them from the equation sheet if you're in an exam. So we're going to do an example here, and we're going to do a second law analysis on a heat exchanger. Now, if you go back and you look at the full long version of the lecture that's posted online, I go through this in all the different ways possible, and I fix all the states. I'm going to try to do that today, but we might not have all the time, or I might kind of flip back and forth between the slides and the Word document once I start fixing states. But we're going to do this heat exchanger problem. Right now, here's our heat exchanger, and what it's telling us, the nice thing is, right, we already fixed all these states, right? We just don't have the specific entropy values. I think we've done this problem already when we were looking at the first law, right? But now what we're trying to do is figure out, is this thing possible, right? So we know the value of the mass flow of the refrigerant, the mass flow of the air, and we know the heat transfer from the air to the refrigerant. So the air here is losing heat, right? That makes sense because its temperature is going down. But then the heat that's going into the refrigerant must be just this same magnitude, but the opposite sign, if we assume that the system is adiabatic, that it's not losing any heat to the atmosphere. So I got the same equations, but today we're going to be focusing mostly here on this second law analysis. So just like when I do conservation of energy, I've got some choices for my control volume. If I have the ability and I'm doing a second law analysis, I want to take the entire heat exchanger as my control volume, if that's possible. If I know enough information to do that, I'll show you why my life gets easier when I do this, right? So here my equation, my second law, So here, if we're trying to figure out, is this process possible, we have to do second law analysis, right? So ds by dt is equal to q dot over T of the surroundings plus the sum of m dot in S in minus the sum of m dot out S out plus this sigma dot term. Now, if you get to a problem, let's say it's the second exam, right? And I ask you, is this thing possible, right? And you're running out of time, write this down, underline this term, and just write this. Say that if this is greater than 0, then that's possible. If it's equal to 0, then that's ideal, right? That's the best possible thing you can do, right? And if it's less than 0, then that's not possible. Obviously, you won't get full credit if you do that, but you'll demonstrate at least that you understand what's going on with the second law, right? What's the purpose of the second law? So we look at this, and now we'll start making assumptions. The reason that I like to do this control volume around the whole system here is because when I do that, the system becomes adiabatic, right? So here, we're going to say that we're at steady state. And because I drew my control volume around the whole system, even though I know that there is some heat going for, oh, I drew this the wrong way. I thought that the tube was the air. So we know that there's some heat going from the air to the refrigerant. When I draw my control volume around the whole system, that heat transfer doesn't cross the boundary of my system. So I'm saying that this is perfectly insulated. Essentially what this means is that all the heat that's lost from the air goes into the refrigerant. I think I spelled that right, but I'm not the best speller in the world. I'm thankful for the red line, right? But the downside of doing this, right? So the upside is I get to get rid of this term, right? This is the term that's often going to give me trouble because here I got to remember this temperature comes from outside my control volume, and it means that I have to take the absolute temperature. So I have to play around with it. I can't put in Celsius or Fahrenheit, right? But if I just can make my problem so that it's adiabatic, I don't have to worry about any of that because this term just goes to 0. So if I can get rid of this heat transfer term, I like to do that because it limits the chances I can make a mistake. Now, of course, I know that, right? So I might craft a question on the exam where you can't do that. But if you can, I think that makes your life a little easier. So if we do this, we're trying to get a symbolic solution. 0 is equal to my inlets. I already know from conservation of mass that the air mass flow rate is constant and the refrigerant mass flow rate is constant, right? So I'm going to separate my inlet and outlet by the fluid type. So here I'm going to say m dot of air times S inlet of air, that's going to be S1, minus the outlet of the air, S2. And then I'm going to add m dot of the refrigerant, right? Because here this was in is positive, out is negative, right? The refrigerant comes in at state 3. This is S3 minus S4. And then I have this sigma dot term. Now, to figure out if something is possible, what I want to do is figure out what the value of sigma dot is. So I want to isolate for that. So I got to move the rest of this stuff to the other side of the equation. Sigma dot, because I like my terms to be positive in my equation, I'm going to move these over and I'm going to flip. I'm going to multiply by -1 in the bracket, right? So I'm still going to have m dot air, but I'm going to make this S2 minus S1 because I've moved it over. Right? We can all agree that that's the same thing as if we just had negative m dot a times S1 minus S2. Right? Hopefully we can all agree on that. M dot R, unless I made a big mistake here. S4 minus S3. So this is our symbolic solution. So we're at the point where this is the thing we're trying to solve for. Right? We know the mass flow rates here are given, but I don't know, I haven't fixed the state, right? So I don't know any of the values for the specific entropy. But if I could fix the state, then I could go through and I could figure out, is this positive or negative, right? So this, you can't get anywhere else on an exam. This is what I would like to see you do. Right? Even if you get to the point where you can't fix the states, hopefully you can get to the point where you've at least done the symbolic solution. You see, even sort of narrating it while I'm doing it maybe took 2 or 3 minutes to do this. And then you can write something like this. I know that if it's positive, then it's possible. And if it's 0, then it's ideal. And it's not possible, right? You don't even have to write all 3 of those things down. You can just say, I'm checking to see if this is negative or something, right? Something that conveys your understanding. So I'm going to go through and fix these states, but only after I show you the other 2 ways that I could have done my symbolic solution here. Yes, Sebastian.
How come you switched the order of S1 and S2 from the top equation to the bottom one?
Yep, that's a good question. So what I did, right, so I took these terms, right, and I was trying to isolate for sigma dot. So I had to move these guys to the other side of the equation, right? So when we do that, right, if this was, if I called this A and this B, right, then when I move them over here, right, this is negative A and this is negative B. Does that make sense?
Yeah, okay. Yeah, I see it. Thank you.
You're welcome. Yeah, so it's, maybe this is, sometimes when you meet engineers, right, you go to their house and they can't deal with a picture being, or maybe they're at your house and you can't deal with a picture being a little bit off level, right? It's just, it just bothers me. I prefer not to have negative terms in my equations if I can help it, right? So this is just a habit of mine, I guess, right? But there's nothing wrong with keeping this as negative m dot a times S1 minus S2. That's exactly the same equation. Oops, we went to the wrong place. So this was for the entire heat exchanger, right? So this is one of my options. If this option is open to me, I would pick this one because I think if I'm going to make a mistake, it's going to be on this term, right? Now, what if I just looked at the air side of the heat exchanger? So now my control volume is in here, just the air part, and it does not include what's going on in the pipe here. Right? So now there is, right, I guess my control volume kind of loops around here, right? So there is some heat transfer crossing the boundary now. So this is Q dot from the air to the refrigerant. So now, again, I would write down ds by dt is equal to Q dot over T surroundings, right? That's the one that's not in the control volume, plus the sum of m dot in S in minus the sum of m dot out S out plus sigma dot. So now if I draw my control volume like this, my assumptions are a little bit different, right? So I'm still at steady state, but now because I'm only dealing with one side of the heat exchanger, there's only one inlet and one outlet, and this term survives. So you may be in a case in an exam where you don't know anything, in this case, about the refrigerant side. So then maybe you'd have to do it this way, right? And then I give you an opportunity to demonstrate that you understand what's going on with this heat transfer term, right? So again, I'll do it in 2 steps so that we can see that I'm isolating, right? So 0 is equal to Q dot. This is from the air to the refrigerant over T in the refrigerant, right? Now, this is going to be plus m dot of the air. Now the inlet, this is S1 minus S2 is the outlet plus sigma dot. And we can call this on the air side, right? Now again, I want to isolate this term. So I'm going to move everything else to the other side of the equation. Now this Q dot term is going to be negative, but I'm going to do this. Sigma dot on the air side is equal to m dot on the air side times, I'm going to flip these around again, S2 minus S1, because I got to multiply by -1 when I come to the other side of the equation. And then this is going to be minus Q dot over the temperature in the refrigerant on the opposite side, right? So here I would have to see what's going on, right? Now the refrigerant is the cold space. Well, here's what you do, right? Because you're going to have some choice on TR. So here's the so here I'd have to fix the states, right? So here, this is what we're trying to find out, trying to figure out if it's positive or negative or 0. I know the mass flow rate. I'm going to have to fix the states in the air, right? I know Q dot was given to me. I got to get the sign right. This is from the air to the refrigerant. So this value here is going to be a negative number, right? Because the air is losing heat. So this is going to be a negative number, which means this whole term I expect to be positive, right? And then I got to make a choice here. Because this is not at some constant temperature, right? This is the place we're transferring heat to. It's not at a constant temperature. So I can pick the lowest temperature or the highest temperature. I think if we went up into our state table, we might have what these temperatures are. But what's going to happen, we have to think a little bit about here. I'm going to do what's called a conservative estimate or approximation, right? Or I want to take a conservative assumption, maybe you'd say, right? Now, this is not a political thing, right? This is about when you make a conservative assumption, right? You're talking about, I'm going to make the assumption so that it's the worst case scenario for me, right? So I want this thing to be positive, right? I want to show that this is a positive number. This, because the air is cooling, remember when we talked about the condensation reaction? As things cool, then we want, what's going to happen is delta S, this change in entropy, is going to be negative because this is cooling. So this first term is going to be negative. The second term is going to be negative times negative Q dot over T. So this second term here is going to be positive. Now, depending on which one of these I pick, I'm going to get a bigger number or a smaller number, right? To be conservative, I want the positive term to be as small as possible. Because if I pick the smallest possible positive term and I find out that this thing is possible, then that means it's possible even in the worst case that I could pick. So here, I want this second term. So I want Q dot over T to be as low as possible, right? So for this to be low, that means I want to pick T of the refrigerant to be the higher value because it's in the denominator. So I want to pick the larger of these two temperatures because this is cooling, or this is heating up, right? We know the exit is 20 degrees. So here I'm going to pick 20 degrees Celsius, which is the same as 293 Kelvin. So that's the number I'm going to put in here, because that's going to make this value lower, which is going to give me a worse shot at showing that this thing is possible. Right? So that's a bit of a subtlety, but I think that, on an exam, I probably wouldn't really grade you too harshly if you pick the other temperature, whatever the saturation temperature here is when you're under the vapor dome at 5 bar. But I think that it's the better assumption for what that temperature is, if it's not explicitly given. So this would be what would happen if, and I guess so the benefits of doing just one side of the heat exchanger are that I only had to fix two states. The downside is this term sticks around. The other downside is just because sigma dot is positive on the air side, I guess doesn't necessarily mean that it's positive on the refrigerant side as well. So we can do just the refrigerant side as well. So here we're going to say this is for the refrigerant side. And now my control volume is just going to be inside this tube. Right, we'll pretend that I boxed all that in. Right, and we got ds by dt is equal to Q dot. Now this is from this is the refrigerant side heat transfer, right, over T. And now outside of my control volume is the temperature of the air, right? So now the heat transfer from the refrigerant's perspective is a positive number, right? Because the refrigerant is heating up, right? And then this is going to be the sum. Well, there's only one inlet and one outlet, right? So this is going to, well, I guess I'll do the whole thing, right? So this is the sum of m dot in S in minus the sum of m dot out S out plus sigma dot on the refrigerant side. Here, this is going to be steady state, one inlet and one outlet. I'll jump to the end here. Sigma dot on the refrigerant side. It's going to look like the other one, right? It's just now we're on the refrigerant side. So this is going to be m dot of the refrigerant times the S out, which is S4, minus S in, which is S3, minus Q dot on the refrigerant side over temperature on the air side. And now here the roles are going to be reversed. So we can see here that this heat transfer term, right, is negative, but I know that my heat transfer to the refrigerant is heating up, right? So that's going to be positive, which means that this whole term is going to be a negative times a positive. So that whole term is going to be negative. And this one here is going to be the positive term. So to be conservative, I want to make this term as big as it can be. So here I want to pick T air min. So the minimum air temperature, which is 22 degrees. So here this is going to be 22 degrees Celsius plus 273, right? Which, if I can do math here on the fly, is 295 Kelvin. So that's the number that I'm going to put in here. I know the mass flow rate. I know the heat transfer, but I got to make sure that I get the right sign. Now I know the temperature, but I haven't fixed the states yet. But if I did, I'd be able to see if this thing was positive. So the thing that's left is to fix the states. So I'm going to come back here. Well, maybe I'll give you a second just to copy this down. And then I'll come back to the slides, and we'll go through how to fix the states. All right. So this, if you remember, was our first law, or our second law equation for the entire system, right? And what we know is we're trying to find sigma dot, right? We know the mass flow rates, but we don't know any of the specific entropies, right? So what I'm going to do is I'm going to start by looking at the refrigerant ones, because those ones, it's just like doing it in water, right? So here, my inlet into the refrigerant happens at a quality of 20% in 5 bar. I stay at 5 bar, but I go up to 20 degrees. So presumably this is going to be a superheated vapor at the outlet, right? So what I do, I draw my TS diagram, right? I have my vapor dome because I'm evaporating something. I start off at state 2 under the vapor dome, right? I know the quality is 0.2. I look here for this. This is the equivalent of table A3, but it's for the refrigerant, 134A. So I don't exactly know what table number it is, but it's whatever that equivalent is that has pressure on the left-hand side. And then I can see that if we're boiling or condensing at 5 bar with R134A, the temperature is 15.74 degrees, right? So S3 is somewhere here under the vapor dome. I know it's closer to the liquid line. So I look here, this table A11, right? I find the 5 bar line, right? And I know that I'm somewhere in between these two numbers, SF and SG, right? And I know that I'm closer to SF because my quality is only 20%. So hopefully this is old hat by now, kind of familiar to you, right? But I can do some math, and I find that S3 is 0.4 kilojoules per kilogram Kelvin. I'm satisfied with this because here I can see that 0.4 is certainly closer to 0.27 than it is to 0.91. Right? So I don't know if I did the math right, but it's in between those two numbers, and it's closer to the lower one, which is what I think should happen. So here I now know S3. S4 for the refrigerant, again, we would find this the same way we would for water. Now we know the pressure is 5 bar and the temperature is 20 degrees. We go to the analogous table for superheated vapor, which would be, it'd be A4 if it's water, right? But we'll see, it's maybe it's A12 here. Yeah, A12. We find the right subtable that has the right pressure, right? So it says 5 bar. Again, it tells us that this refrigerant boils at 15.74 degrees, but we're at 20 degrees, right? So it's nice. We don't even have to interpolate. We would just pull values from this table. And the only thing we need here is the specific entropy. So I know S4, right? So I do S4, I put it in here. Right now, the thing is, how do I find S1 and S2, or if I'm doing constant specific heat analysis, how do I just find this delta, right? Because now if I look at this equation, I know everything except S2 and S1, the air side specific entropies. So we go back to what we talked about already, right? So there's different ways that we can find specific entropy for ideal gases. I can use the tables, right? And in this case, I know the temperature, and I know the pressure. So I could use this equation, right? I just have to look up S superscript 0 values on table A22. And over here, I have two options for constant specific heat, but I don't know the specific volumes of the gas, right? So I can't really use, I can use what's called option B in this particular list, right? But I can't use option C because I don't know the specific volumes. Maybe I could use the ideal gas law to try to figure them out, but why go through the effort when I can use option B? There's no difference in accuracy between B and C, these constant specific heat relationships, but option A is more accurate than option B and C, right? But here we can't really use C, right? So I'm going to start off doing this with variable specific heat, right? Because I want to show you that's kind of the newest thing to do here, right? I have to remember first that delta S is not the same thing as delta S superscript 0, that's just part of the answer. So here I know my temperatures, but I got to change them to Kelvin because here it doesn't say, you'd have to look at the header of this, but temperatures here are in Kelvin and not Celsius, right? So here I find that 305, it's exactly on my list. So I see S superscript 0 here, I get a value. For state 2, I know that my temperature is 22 degrees Celsius. Again, I have to convert that to Kelvin, right? And I get another value for S superscript 0. I know those two things and I put them into my relationship. Now, here we're also given pressure, so that means this term is going to survive. So I have to evaluate that term too. But I believe I was given the specific gas constant, or I could take the universal gas constant and divide by the molar mass of air. I have P1 and I have P2. So I can plug all this into my equation. I got to make sure that I don't fat finger it on my calculator, which again, I'm really good at doing. I would evaluate it like this as two different parts, because again, I'm really easy. I know you can put it all into your calculator at one time, but I'm really good at messing up the order of operations of that kind of stuff too. So here I get a number for delta S for the air side, right? So here now I have values. I can put these all into my equation because now everything's golden, right? I have all the information that I need except for that thing that I'm trying to find, right? So I can put all of these values into my equation. Again, I'm evaluating each term, right? So here I'm going to check my units, right? Because my mass flow rate is in kilograms per second. You got to be careful because it could be in kilograms per minute, right? And I get here an expression, right? Or a value here for the, so this is the entropy generation rate on the air side. This one's negative, which makes sense because the air is cooling down. We expect this part to be negative. But we want this part here, because the refrigerant is heating up, we need it to be bigger than the entropy, the reduction in entropy on the air side, right? So here we put in some numbers here, and we can see that this is, again, the whole thing is positive, right? So this is just like, remember I was talking about this with my brother, that the entropy of a fluid can decrease in a process, right? That's what happened to the air because it cooled down. But the entropy of the universe, the entropy generation rate, has to be positive, right? So this term was negative, but this term was positive and had a larger magnitude, right? So that's our answer if we got this just on the in the whole system, right? And again, remember, this is, I like to do it this way if I can, because then I get rid of that heat transfer rate term. But I can also do this without the tables, right? I could also do this with constant specific heat. So then here, I think I switched these around versus what's in the equation, right? So this is S2 minus S1. I'm going to pick the equation that has pressures in it because I know the pressures and not the specific volumes, and I don't want to go through the effort of the ideal gas law to figure those out because there's a lot of unit problems I can have by doing that, right? So I'm just going to not do that, right? And now I put my values in here. Again, I know my temperatures, but my temperatures have to be in absolute temperature. They have to be in Kelvin, right? I know my pressures. These are absolute pressures. So I put these in. I get that this first term is negative. And I work out the second term. and it's also negative, but this is like the negative of a negative, right? But on the whole, this part with the air is negative, right? And again, that's what we expect because the air temperature is decreasing. So we expect the specific entropy change in the air to be negative. So we're not worried yet, right? Because this is just that first term in our equation, right? And here you can see because our temperature difference was pretty small, right? I think it's like on the order of 15 or 20 degrees. Then the constant specific heat answer is actually pretty close to the variable specific heat answer. The divergence here gets bigger and bigger as our temperature change gets bigger and bigger. Right? So here, right? So this, I could then take this value and I could put that back in to the other equation. And again, I would see that the whole thing is possible. Right? This was the analysis on the air side. I think the slides go through the whole analysis, so I'll go through that quick, and I'll show you that we can also show that the, right? So this is all the same numbers, right? So now we've already fixed S2 right here. I think I'll just skip to the end because we're running out of time, right? So here, if we go to just the air side, right, we can see again that the total entropy generation rate here is, that's just the, sorry. Right, so here we get on the air side, because the heat transfer is leaving the system, right, and this was negative Q dot up here, that this term that's related to the heat transfer ends up being positive, and the term that's related to the change in the entropy in the air is negative, but the magnitude of this term is bigger, right? The positive term is bigger, so sigma dot is positive. So that means the air side looks good. If we just did the air side by itself, then it's possible. I can do just the liquid side by itself, which we also showed how to generate this expression. And now again that I fixed everything, right? We picked here the lower number here because we want this negative term to be as big as possible. And we find that this one, again, just ends up being positive, right? Positive, but just barely, right? So here, this is really close. So if I was just doing this, maybe I'd want to use a different method too, just to double check that this is really positive. Because this is positive, but it's pretty close to being negative. So, if you were designing something, you might want to go back and look at the assumptions that you have here, because if you pick some assumptions that aren't conservative here and you're just barely positive like this, then it might be that your assumptions are making it look positive when it's really not. So that was all that I wanted to talk about today. Did anyone have questions or things that they wanted to discuss? All right. If not, I will see you tomorrow, and have a good day. Bye-bye, everybody.